Question 4 is all about fields. In an electric field, 6 microjoules of work is done to shift a particle with a charge of 0.15 microcoulomb from a starting point to a final point. What is the electric potential difference between these 2 points? So in this question, we have been given the amount of work that has been done to take a particle from one point to another point. How much is the work? The work is given to be 6.0 microjoules. Okay, we have also been given the charge of the particle, which is 0.15 microjoule. And we are supposed to find the potential difference. Now, if you go to our data booklet, we see this equation. Work done equals the charge times the potential difference. So we're going to use this equation. Work equals charge times potential difference. This equation can be rearranged for potential difference. That gives us potential difference equals work over the charge on the particle. Now, all we have to do is to sub in the value. So we want to sub in the value for work, that goes here, and we want to sub in the value for the charge. So let's try and do that. So that would give us work, the change in potential equals work, 6 microjoules divided by the charge, which is 0.15 microcoulomb. Okay, if we do this, we can write this as 6 into 10 to the minus 6 joules divided by 0.15 into 10 to the minus 6 coulombs. This cancels away, and this will turn out to be 40 volts. And that solves the first part of the problem. Let's move on to the second part of the problem. A particle A carrying a charge of 50 microcoulomb is held in a fixed position. A second particle B with a charge of plus 440 microcoulomb is initially held at a distance of 60 centimeter from particle A. Particle B is then released, and we are to find the initial electrostatic force experienced by particle B the moment it is released, and we are supposed to give a description of the motion of particle B immediately after its release. So what we have here is we have a stationary charge that is 50 microcoulomb. Okay, that's stationary. And we have another particle, another charged particle, whose charge is 0.40 microcoulomb. And they are separated by a distance of 60 centimeter. So I'm going to write that in meters. And we have to find the force. First of all, we realize that both of the charges are positive. So there's going to be a repulsion between them. The charge over here is going to be repelled away. And that can be found, the force of repulsion can be found using Coulomb's law. Coulomb's law is given in our data booklet over here. K Q1 Q2 over R square, where K is itself a constant equal to this particular quantity. So let's write Coulomb's law, which is F equals K Q1 Q2 over the distance separating them. Okay, the value of K, it's about 8.9 into 10 to the 9. Q1 is 50 into 10 to the minus 6. Q2 is 0.4 into 10 to the minus 6 divided by R square. That would be 0.6 square. So all we have to do is plug this into our calculator and we'll get the result. The result will turn out to be about 0.50 Newton away from charge A. The qualitative description would be that due to Coulomb's repulsive force, we know that both of the charges are positive, so there's going to be a repulsive force. So therefore, as soon as we release this charge, it's going to accelerate away from charge A. And that solves this part of the problem. Let's move on to the next one. Two long parallel conductors, conductor 1 and conductor 2, which carry equal currents directed out of the page. So there are two current carrying wires that are moving out of the screen. At point P is located such that it forms an equilateral triangle with the points where the conductors intersect the page. So we have two current carrying wires. This is wire 1 and this is wire 2. And these wires are coming out of the screen. And there's another point, point P, such that the triangle thus formed is equilateral, meaning all of the sides are equal. We are also given that the magnitude of the magnetic field at point P generated by conductor 1 alone is 20 millitesla, meaning that due to this current carrying wire, the magnetic field over here is 20 millitesla. On a diagram, sketch the arrangement, which we already have, and draw a vector representing the direction of the magnetic field at point P due to the current in conductor 1 alone. So we have to draw the direction of the magnetic field due to this conductor. So what are we going to do? You must remember that we can find the direction of magnetic field in a straight wire conductor using the right hand rule. So the magnetic field due to this wire is going to be counterclockwise in circles. And the magnetic field at a particular point, at point P, will be a tangent to the circle. So I'm going to draw the tangent to this circle. That's going to pass like this. And this force is given as 20 millitesla. Okay, so that solves this part of the problem. The next part says find the magnitude and describe the direction of the resultant magnetic field at point P due to both conductors. Now this sketch that we drew here, it was the magnetic field due to conductor 1 alone. What about conductor 2? Well, we do the same thing again. Conductor 2, the magnetic field would be around in circles like this, right, due to the right hand rule. But if we want to find the magnetic field at point P, it's going to be a tangent to the circle. Okay, so let's draw that. So this would be the tangent to the circle. And what would be its magnitude? Well, since both the conductors carry the same current, they are at the same separation. Therefore, this must be 20 millitesla as well. Right? Now we want to find the total magnetic field. So what should we do? Well, the best way to do this is to take the components. What to do is, I'll draw a dotted line. And I know this angle here is 60 degrees. I'm going to take the component of this vector along the horizontal. Okay, that's going to be 20 millitesla times cosine 60. We can do the same with this vector. We can break it along the horizontal, and that horizontal component would be the same term, 20 cosine 60. This term must be multiplied by 2. But what about the vertical components? Well, if you take the vertical component of this and the vertical component of this, these two vectors cancel one another. So the vertical components cancel, the horizontals add up, and the total sum is equal to this. This will turn out to be 40 times 10 to the minus 3 times cosine 60 is 1 over 2. And that is 20 millitesla to the left, horizontally to the left. So the total field at point P is going to point along this direction. And that completely solves the problem. I'll attach the PDF in the description. Right now I'm accepting new students for the new academic year. If you're interested, drop me a mail. I'll see you in the next one. Happy learning.